Okay. 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 Good morning, students. Let's begin lecture. We're going to do some angular momentum demonstrations. You may have seen me with Darian and Caroline and the two students in the front getting ready. We'll do that in a minute, but before we do, look at those demonstrations for which you can also view past semesters in YouTube. I'm going to videotape. Do not let me forget to videotape. We're going to videotape today too and put it on YouTube. But before we do that, I want to go over office hours. We have an exam coming up next Tuesday. Okay? And so this is when office hours becomes an important study strategy and a study resource. Now, mine are the same as always. We'll be meeting tomorrow, 9 o'clock to 11 o'clock in the morning in room PS 158. And that's just off the atrium of the Physical Sciences building. Now, Caroline has office hours on Friday, 1:30, right? Everything's good this week? Mm-hmm. All right. And so she'll be there and in the atrium, and she'll really help you out. The other thing I noticed is that the SI schedule is actually perfectly configured to have, if you think about it, 4 study sessions between Thursday lecture and next Tuesday's midterm. You have one Thursday at 1:30, so that's right after my noon lecture, then one on Friday, and then 2 on Monday, and then Tuesday you come in here and write the exam. Now this week we're going to be mostly talk. You ready? Okay. This week we're mostly going to be talking about heat and thermal energy and stuff this week. So what you want to do is be able to pay attention to everything and then prepare for the exam on Tuesday. Now, another thing I want to mention to you before we start the main part of the exam of the lecture is that I'm going to open up and activate a special web courses section for the General Education Program Assessment, GEP, and it's got its own designation, and you'll see it on your your site, your to-do list or something like that. There's a quiz in there called Diagnostic Test, and you guys will be able to go in there, and it's like a 10-15 minute chore, answering a bunch of questions, and get that done. You click on it, and this is what the front page looks like, and just get that out of the way. It's not part of your semester grade for this class. It's open to all students in Physical Sciences 1121, whether the lecture classes or the online sections, and it's just a way for the university to do planning and kind of assess things that are happening and stuff. So do your best and don't sweat it if you don't get a perfect grade, because you probably won't. But it'll give us a snapshot that we need for planning and stuff. So you'll be able to see that after class. So maybe 1:30 or something like that. I think I have it set. All right. Now let's do some angular momentum demonstrations. I'm going to pause the podcast. Okay, now we just went over the 2 angular momentum demonstrations. The first one is the student changing the position of the hand weights on the stool. So let's go over that. And as I mentioned, the key here for Miss Vanessa is that there's very good quality ball bearings underneath the lab stool. So she's actually spinning on the lab stool. And there's some diagrams on page 86. This is a diagram that I made, and I swiped it from my own book. Okay, so number 2. The student pulls each mass in, okay, to a smaller R. Now, each of those hand weights are about 2-point-something kilograms. It's marked 5 pounds. Right? So you got 2-point-something kilogram left and right. And when she started with them out here, and she brought them in chest high, she really started to spin up. Now, the reason for that, the moment of inertia of the hand weights changed. Now, her moment of inertia changed a little bit because her arms came in. But most of her moment of inertia is in her body. That's where most of your mass is. But the thing that did change are the two hand weights. So we're talking about the change in the moment of inertia. 2mr squared is smaller because r is smaller. And since that's smaller in the moment of inertia, the omega, the angular velocity, has to increase. So she gets a faster spin. And that's in order to keep the angular momentum constant. Angular momentum is L equals I omega for something that's spinning with angular velocity omega. So if moment of inertia, capital I, decreases a little bit, which she did when she brings her hands in, I has to go up a little bit. And it goes up just enough to keep angular momentum constant. All right, now the other case is this. When she starts with the hand weights in, about chest high, and then she extends her arms out, so she pushes them outward. All right? And when she does that, she puts them out to maximum R. All right? And it's not easy, is it? I mean, it takes a little bit of muscle power to do that. It's you don't know it until you get up here, and I'll bet you felt the same way. It's changing the orientation of that wheel is not easy. Anyways, so she's at maximum R. That means 2mr squared from the hand weights. And that's the part of the moment of inertia that's changing significantly. 2mr squared. That's going to be a little bit larger because now her R is maximum. Okay, so right in here, her R is a few centimeters when it's in chest high, right by her heart. But then when she extends her arms, it's out to, maybe half of a meter left and half of a meter right. So R squared is bigger, 2mr squared is larger. And so omega has to decrease in order to continue keeping the angular momentum constant. All right? So this is what I like to call the ice skater effect. And you've just seen Miss Vanessa demonstrate that. All right, now I want to pause for a question. Okay, let's keep going. I want to go over something from the textbook called the right-hand rule, and it holds for angular momentum and other things. And it is the way in which we determine the direction of the arrow that we use to represent angular velocity or angular momentum or even torque, which is the change in the angular momentum per second. So what you do is you curl your fingers of your right hand in the sense that the object is spinning. So now, if you remember, when we were using the bicycle wheel, I motioned, in fact, with my whole arm in the direction of the bicycle wheel spinning. We always started with it rotating from right to left across the front. And now, if you do that with your fingers, your thumb of your right hand points in the direction that the angular velocity vector, omega, the angular momentum vector, capital L, and actually the torque, if it's accelerating, if you're actually applying a force, you can use this to represent the direction of the torque vector. So they all point in the direction of your thumb. And it's related to the sense that something is spinning. All right? And this is going to help us understand the transfer of momentum that Stefan experienced, when he flipped that bicycle wheel. Because the bicycle wheel, if you think about it, the bicycle wheel was spinning this way, but after he flipped it, it was spinning the other way. All right? And so he had a big change in the angular velocity and a big change in the angular momentum. Now, before we go and talk about Stefan's demonstration, let's do a simple example by thinking about the Orlando Eye. Raise your hand if you've ever been on the Orlando Eye. Just a few of you. Is it expensive? Like $50 or something?
You can do like the 360 for about that.
360?
No, like there's the Wax Museum and the aquarium, so like you can pay for.
Oh, for all three of them for $50. I see. I haven't been up to it. Anyways, Orlando Eye. And I spent like an hour figuring out what direction it spins. So if you're looking at it from the west and you're looking east, it spins clockwise. So go ahead and make a sketch, of the Orlando Eye. And I like this. This is an aerial photo. It must have been from a drone or something, maybe a helicopter. And it's just about the right level, the same level as the hub of the Orlando Eye. In other words, the spin axis. This person, this observer who took this photograph, was sitting right on the spin axis. All right? Now, let's think about the right-hand rule here. The right-hand rule, if you take it from this perspective, the right-hand rule is going clockwise, as I'm doing with my hand. Okay, so maybe you should try doing it. Now, don't use your left hand, use your right hand. I inadvertently saw somebody using their left hand, but I've done that myself too. I remember in grad school, one time I was working on this angular momentum problem or something, or magnetic field problem, and I kept getting it wrong. And I said, no, this has got to be right. I've got it. And I checked, and what I realized was I was writing with my right hand, and I was doing all the directionality with my left hand. And then when I figured out what I was doing, I, face palm, and then I figured it out. So anyway, so your right hand, it's going up and over clockwise like this. So that means that the angular velocity vector is into the screen. Now, in this view, into the screen means it's also pointing to the east. But the symbol that we usually use to represent a vector pointing into the paper or into the computer screen is a circle with an X in the middle of it. And that's this one down here in the bottom of this second yellow panel. Now let me do a big version of it. And where you would draw your angular momentum vector is right up here, all right, at the center. So it's going to be along the spin axis, and it's going to be pointing into the computer screen. Or if you're actually there, it would be pointing east. All right? And that's if you're looking at the Orlando Eye from the west. Now, if you're behind the Orlando Eye, on the other side of it, it's going to look different. But this is how... Now, let me ask... You're going to be figuring out one of these problems here in a second, deciding on directions. So let me pause for questions. Go ahead. Yes? That's correct. The circle with the X in the middle of it, it's supposed to symbolize the feathers on an arrow as it moves away from you. The symbol that we use for a vector coming out of the page or out of the projector screen is a circle with a dot in the middle. And that's to represent the tip of the arrow that's coming towards you now. So you want to get out of the way a little bit. All right? But that's the two symbols that we ordinarily use. But and that's only if your perspective, if your sketch is, face on like we are here. If you're in perspective, it's a little different. Now, we're going to do a perspective view, and I want you to think carefully about this because we're going to go behind the Orlando eye. Okay? Now, from the other direction, here's a picture of a guy looking at the Orlando eye from the back side. You know, so it's like the service entrance. You know, all the trucks go in there and stuff like that. Okay? And so if you curl the right hand of your finger in the sense of that big white arrow, that's the direction that they're moving. All right? And then your thumb is pointing now kind of, in this view, it's a perspective view, so it's pointing out and kind of off to the right, to the left a little bit. All right? So the only thing that is different here is what you would normally do is sketch it up by the hub of of your diagram. So let's do a sketch of that. Go ahead and, this one you can make a sketch. Okay, so here's your Orlando eye, and here's a couple of the gondolas right here. Sketched them in. And they're about, this is about the right spacing. So I think there's 12 degrees between each gondola. And the sense of rotation is here. Now notice that I made the front of it that's facing you a little bit wider than the back. Okay, here's the back over here. All right? That's away from you. And this side here, it's a little thicker. That's the side that's moving up, and it's a little closer to you. So this is a perspective view. All right? Now, on this one, you can still curl your fingers in the direction of the blue arrow, and then your thumb is going to be coming out. But because it's a perspective, it's going to look about like this. All right? And again, what I've done here, notice that my yellow arrow obscures the back of the wheel, the downstroke of the wheel. And that's the side that's coming downward now. You're coming back to the base. I've obscured that with my yellow arrow to represent depth. Okay, so the arrow is right at the hub. The tail of it is right at the hub, and it's pointing in the right direction. And that is consonant with this hand down here in the lower right that shows the right-hand rule. Okay, so they're both oriented roughly the same way. All right. Now let me pause again for questions. Yes. They're both, you mean the yellow arrow? That's the angular velocity, omega. It's facing the right direction. All right, see where my hand is? This one? What vector arrow? This one? Oh, this? Oh, that's to symbolize that it's a vector. I'm sorry. Yeah, you know how like I put like a net force, when I put a vector symbol, it's a little tiny arrow over the top. This is a lowercase omega, so it looks like it's floating out there. But so sorry about that. You're talking about this guy here right above the omega. Yeah, that's just to symbolize vector. Okay, another question. Okay, let's keep going. Now we're going to do a clicker question together. And again, I'm going to give you a different system that's spinning, and it's going to be in perspective view. All right, and what you're going to do is decide on the direction of the angular momentum vector using the right-hand rule. Okay, so turn on your clicker. Devin. Is your clicker going? It's Devin, right? Yeah. Right. Clicker's good? All right. You didn't type in your answer yet, did you? Good. Because I didn't give you the question yet. Here's the question. Okay, in this perspective view, the merry-go-round spins as shown by the yellow arrow. Right? What direction is the angular? And so I've got 4 different arrows, alternating colors. And then E is if you decide, nope, I don't have enough information. Not possible to tell. So use the right hand that's on the right side of your body. Right. You know, sometimes I see, you know, like on exam 2, I'll see students on, you know, because you're going to have a question about this on exam 2, right? There's going to be right-hand rule. You're going to have to make a decision like this. And if I see it's every once in a while I'll see a student, you know, doing this with their left hand. And the only time I ever help a student on a test is if I see that. All right, I'll tell, no, right hand rule, right hand, the other right hand. All right, so go ahead and answer your questions. Okay, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Click. All right, let's display that. Okay, now the correct answer is C, and the majority of class barely voted for that. Let's take a look. Go ahead, back to the regular display. Thank you. All right, so the answer is C, and the reason for that, if you think that, now I'm going to curve my hand, all right? So my hand is now curving in front of the merry-go-round in the same sense, my right hand is, as the merry-go-round is spinning. So that means my thumb is showing the direction of the angular velocity and the angular momentum. Now, side note on this question, I hope you've drawn a little sketch. Because in this sketch, if you were pushing on this thing, you know, from, you know, like kind of like Caroline and Darian and I were trying to spin up that wheel, and we were exerting a force tangential to the wheel to get it to spin. We were exerting a torque. If you were exerting a force from left to right on this thing, your torque, you'd be causing a spin, or an acceleration anyways, in this sense. And so your torque would be represented with an arrow that's upward. All right, so that's that. Now, this is a brain burner question. Right, and I want you to write it down in your notes. Think of it as a notes, a section of notes. And this is Stefan's demonstration. If a student initially, without spin, L subscript S, the student's angular momentum is 0, which is what he started with, he takes the wheel with a positive 20 kilogram meters squared per second. Now, I don't know what the exact angular momentum is. Okay? So I'm just assuming it has a good old 20 kilogram meters squared per second. All right? So that's the angular momentum of the wheel. And that is because I made sure that we always spun it up so that it would be spinning from left to right in the front of the wheel. Okay? So the initial angular momentum is upward. And I have the spin axis, a little thin line there you can see in front of all the arrows and stuff. So there's the spin axis. And then when Stefan flipped it upside down, now it's spinning the other way. And so, you know, he went from this to this, all right? So it's still spinning. And it took a little bit of muscle power to do that, right? All right? So he went from plus 20 to minus 20. Or no, he didn't. The bicycle wheel did, all right? So how much delta LS does he have to acquire? Go ahead and vote. And think. Think very carefully. This is what we call an interaction. A spin interaction. And believe it or not, there are buku scientists trying to figure out quantum spin systems for running computers. Right now, we just have electrons floating around and stuff. But what we really want to be able to do is to do spin flipping. Spintronics, they call it. And when they can get a good system of that going, it's going to really speed up computers. All right. That's interesting. Okay. 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3. Come on. 2, 1. Okay, 0. All right, I want them to see this. All right, no clear winner here. There is a clear answer. This is pretty much a random spread of answers. So let's get you guys away from random and slotted you in, and let's get you slotted into the correct situation. All right, go back to regular. Thank you. All right. So the correct answer is 40, positive. Who voted for 40? Good. If you voted for 40, that's mainly people over here. This must be the, let's see, this is the port side of the room. If you're facing forward, that must be it. Let's look at delta L for the wheel. All right. That's the final angular momentum of the wheel minus the initial angular momentum of the wheel. L subscript FW minus L subscript IW. Now I did put any little arrows over the top here, but we're using pluses and minuses for upness and downness. Okay? Now, the final angular momentum is downward, so that's a minus sign. Okay, so minus 20 kilogram meters squared per second. And then the initial was positive, so I subtract the initial, so that's minus 20. And that's a total of negative 40 kilogram meters squared per second squared. So the wheel acquires, when Stefan muscles it and flips that thing over, it acquires negative 40 kilogram meters squared per second. And therefore, he acquires positive 40. And that is why he began to spin in the direction that he did. Right? And when I publish this on YouTube, you'll be able to go back and look at that. All right? So the bottom line here for us, the student and wheel demonstration that Stefan did, exchanging plus or minus delta L, yeah, that's really similar to the skateboarders pushing off each other. Now the skateboarders, it's plus or minus delta P, a certain amount of linear momentum. P equals mv momentum. For us, it's L equals IW angular momentum, plus or minus. Right? So I have a feeling that these two guys, Sir Isaac Newton and his boss, Professor Galileo, would have been really, really thrilled to see that. I doubt that even Sir Isaac Newton was able to observe that demonstration. But it's important for us. It is an interaction. It is a spin interaction. And as I mentioned, the entire physical world is modeled on the idea of interactions. And this is another kind of an interaction that physical objects can undergo. It's profound what you guys just saw when you think about it in terms of the quantum world. All right, now at the end of chapter 5, I finish up with a short description of something called a phase portrait. This is from page 88, and we're going to continue talking about phase space and phase portraits for the duration of the semester. And the reason for that is that phase diagrams, phase portraits in phase space are one of the best ways of understanding why the quantum world is quantized. You know, we have the atoms and stuff the electrons orbiting the nucleus of atom, they can only have certain energy levels. You know, a basketball can assume any energy level on the way down and back and on the way back up. But electrons, no, they can only have certain quantized, numbered energy levels. And nobody really understands why that is. But we know one way to generate it, and that's through the use of phase space. If you think about it, the units of area of this, go ahead and make a note of this, phase portrait in phase space, the units of area here, remember when we did that velocity graph? And I said this is an abstract graph, and the area units were distance, meters. In this one, the area units, a momentum times a distance, is angular momentum. And so for some reason, thinking about a quantum system in terms of angular momentum is incredibly powerful. And it is everything in the quantum world. And so, as I said, there's a lot we're still working on. You know, we're still working on the really cool quantum systems. So maybe one of you or one of your grandchildren will nail down the final nail, but we still have a lot of work to do. And this is one of the best starting points for it. Okay, let's talk about chapter 6. And speaking of spinning systems, look at this. This was on Astronomy Picture of the Day 2 days ago. Sunday, I guess. It is a picture of a supercell thunderstorm in Montana, eastern Montana, out by Glasgow, Montana. And that's my old stomping grounds out there in Montana, so I really love this picture. Can you imagine if you're in a car by yourself? And you know, eastern Montana, it's very sparsely populated. So you're out there in the middle of eastern Montana, there's no cars around. And there's like one building. See that one building there? And you see this storm coming at you. And okay, see you later. And just last night you were watching the X-Files or something. And you're thinking, oh no, that's the aliens coming to get me. Yeah, there's storms like this. I've actually seen storms a little bit like this last time I drove through the Everglades, you know, coming up from Fort Lauderdale and through Palm Beach and stuff. So, and this is a thermal system. This is a thunderstorm. So make a note, thunderstorms, yeah, we get tons of thunderstorms. They are thermal systems, and they involve convection, heat transport, phase transitions, everything that we're going to be talking about in this chapter. Now, we're not going to be modeling thunderstorms. Hardly anybody can really do a good model of them. They're very complex, very difficult to model. But yeah, there's all kinds of cool thermal features to a thunderstorm. So let's get down to some of the basic concepts. And we're just going to do a little overview here of the three main things that we're going to talk about in chapter 6. First of all, stirring up water, adding kinetic energy to it, leads to an increase in temperature. Now, we've measured that. James Prescott Joule was able to measure that back in the 1800s. And in chapter 6.3 and through there, you'll read about the kinetic theory of matter. The kinetic theory of matter is basically saying, all the 1/2 mv squared kinetic energy of all the particles of water, all the molecules, adds up to a certain number, and that's proportional to the temperature. It's kind of a cool theory. Another thing that we are going to talk about is two objects that are at different temperatures. They're not at thermal equilibrium. And when you have that, you get heat transport of various kinds. You can have conduction of heat if you have thermal contact. So if you take an ice cube in your hand, the heat from your hand is conducted into the ice cube and it melts. If you take your shoes off down at the beach and you go walking across the sand at 2 in the afternoon, your feet are going to get baked instantaneously because the heat from the sand is going to conduct into your toes. All right? Now it's not going to, your hands are up here in the air, and the air is not conducting much. Air is a good insulator. It doesn't conduct. So the air might be even hotter than the sand, but your hands are not in contact, but your feet are in contact with the sand, so your feet get burned. Can you get sunburn on your feet from walking on the... Gosh, that would be miserable. I've had some bad sunburn, but... Anyways, different elements and molecules cool off and heat up differently. Now, this is what we're going to be tackling today, the phases of matter. So this is Chapter 6, Section 2, and actually it's all through Chapter 6 that we're going to be talking about this. All right, and what we're going to be doing today is the famous heat melt heat problem that every semester we work on. It's been traditionally one of the toughest brain burners in Physical Science 1121. And we're going to start talking about it today. How do we start talking about it? Well, let's talk about the Kelvin temperature scale. This is the scientific temperature scale that scientists tend to use. It's based on Celsius. It's a metric. It's considered a metric system temperature scale, but it has a different baseline temperature. Okay, so Celsius, and here's a picture of Lord Kelvin. It's named after Lord Kelvin, whose first and last name are William Thomson. And he became a lord over there in England back in the 1800s, I guess. And he was a very smart scientist. Anyways, the freezing point of water is the 0 point for Celsius. No 0 Celsius is freezing. Now, we don't see those temperatures around in Orlando. But a little bit further north, yep, you'll see freezing, 0 Celsius. Anybody from, does it ever get freezing in Jacksonville?
I think occasionally, but not really,
Not that often. Hardly ever here either. But not too much further north from Jacksonville, up into Georgia, yeah, you can freeze your patooties off. Okay, and that's 0 Celsius. Now, for the Kelvin system, 0 is colloquially known as the point at which all molecular motion ceases. So I just mentioned, the kinetic theory of matter, all those 1/2 mv squareds of all the molecules zipping and zapping around, they all add up and it's proportional to the temperature. So everything has motion. We think, the molecules of nitrogen and oxygen that you're breathing right now, we can't see them. They're so small, but there's zillions of them. Your lungs can handle them. Your nose can process them and get them into your lungs. Then your lung will put those atoms into your bloodstream and stuff like that. But we can't really see them, but we know that they're zipping around at very high speeds. All right. Now, as the temperatures decrease, things slow down. In fact, you can get water vapor to cool down enough, it'll form a droplet of water. Cool it even more, even lower temperature, there won't be moving around hardly at all because it's an ice crystal. It's locked in a crystalline solid, right? Now, but even an ice crystal, they have a little bit of, they're rattling around in there. They're able to, shake their cages a little bit, so they're still in motion. Right? But theoretically, there's a point where all motion ceases, and that's called absolute 0. The best way, however, to define it is this. It is the point at which no more work can be extracted. Now, if you're thinking about extracting work, what that means is if you think of a steam locomotive, or your internal combustion engine, you create heat, it moves a piston, and the piston is connected to your drivetrain. Your drivetrain moves the axle, and the axle moves your tires. And they're in contact with the road, and the road pushes you forward or backwards, depending on where you're going. Okay. So a heat engine, like your internal combustion engine or steam locomotive or anything like that, has to be able to do work for it to. It has to have heat energy for it to be able to do work. But theoretically, there's a point at which no more physical work can be extracted, and that's called absolute zero. Now, here's the set of temperature scales, Kelvin, Celsius, and Fahrenheit. We'll just talk about them for a second. And Fahrenheit, 32 degrees Fahrenheit, 212 Fahrenheit for boiling point. We're not really going to use Fahrenheit. So, and you know what, guys? I hate converting from Fahrenheit to Celsius. So you're never, ever going to have to do that. Okay? So just go ahead and X that out. So we'll just talk about these two, Celsius and Kelvin. I mean, Fahrenheit you hear on the weather report or the Weather Channel, Eyewitness News, weather and stuff like that. Celsius too. You hardly ever hear Kelvin. But everywhere else in science, you talk about the Kelvin scale. Okay, 0 in the Kelvin scale is negative 273 Celsius. All right? So the 0 of the Celsius scale is oriented to water, but the 0 of the Kelvin scale is oriented to zap. No physical work extracted. Steam engines stop, or heat engines cease to work and put out work for you. All right? And it's 273 Celsius degrees below freezing point of water. Therefore, positive 273 Kelvin is the 0 point of Celsius. All right? And so, by the same token, the boiling point of liquid water, 100 Celsius, all right, that's 373 Kelvin. Right? So whatever your Celsius is, add 273, and that's your Kelvin temperature. Whatever your Kelvin temperature is. Now, I'm going to be doing Kelvin, 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 Kelvin. But you'll see different textbooks and stuff that you may use working in Celsius and Kelvin. But I tend to work only in Kelvin. All right? Now, let me pause for questions about this Kelvin temperature scale. Okay, let's keep going. Let's do a little simple workout with Kelvin temperature scale concepts. All right, get your clickers out. Here's question number, what are we on?
3.
Question 3 for today. Okay, room temperature in Celsius over in the chemistry department is generally considered to be 20 degrees Celsius. Now, what is that in the Kelvin scale? And I believe that would be 68 Fahrenheit. Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, most of you got this one right, 293. Sometimes you see 300 as room temperature. That would be kind of hot. But it's a little bit more of a round number than 293. So let's take a look at another question. Now, this one I want you to think about. Question number 4. An advantage to the Kelvin scale compared to Celsius. Now, I'm going to be marking this one carefully. Think about it. Read carefully. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ching. Yeah, most of you guys got that right. So now the reason that we like this is because the idea of the kinetic theory is that the total of all the kinetic energy of all the molecules that you cannot see. Now we can figure out the sum of all the kinetic energies and the average and everything. Supposedly that's proportional to the temperature. And so since kinetic energy is always positive, it's good to have a temperature scale that's always positive. And that's why we like that. Now let's talk about some more heat-related phenomena. Here's a picture of a star. Betelgeuse. It's a red supergiant. And if I recall correctly, I believe it is the right shoulder of Orion. Now, if you don't know Orion, the constellation, Orion is the hunter. He has a belt of 3 stars, and he's up at night right now. You get up after dinner. When it's good and dark, 9, 10 o'clock, you'll see Orion right up close to the top of the sky. And Sirius, the brightest star in the sky, is a little bit down and to the left of him. And Betelgeuse is a supergiant in the shoulder of, and I think it's the right shoulder, if I recall correctly, of Orion. Now, why do we call it a red supergiant? Well, it's red. You can actually see it. It looks red to your eye. It's one of the stars that looks red. It's bright enough that we can make out its color. This is actually a picture of the surface of Betelgeuse. It's close enough and big enough that we can actually see those bright spots in the middle of it, the 2 big bright spots. Those are really hot areas. Those are like sunspots. Those are similar to sunspots. If you're close enough to Earth, you probably can detect the presence of big sunspots. Not the little ones that Galileo saw, but every once in a while there's some really big ones. And I bet somebody on Alpha Centauri, which is pretty close to us, they could probably make them out if they have good if there's life there. If you ever went to Alpha Centauri with a good telescope, you could probably make out our sunspots. But Betelgeuse is so big, we can make them out. Hey, you guys. The color of Betelgeuse tells us the surface temperature. The color of Betelgeuse tells us the surface temperature, a certain number of kelvins. Second, the structure that you see on the surface, cool here, hot there, is convection, one of the heat transport methods. So it's kind of cool, if you think about thunderstorms on the surface of Earth being huge convection systems, even bigger convection system is a hurricane. Oh my goodness. and they can be really big. Okay, on the surface of Betelgeuse, yeah, and the same thing on the surface of the sun. Sunspots are usually involved with convection. Here's another thermal concept. This is a star cluster known as M13, and I don't know if you can notice it, but if you look at the YouTube, you'll be able to see that there's a lot of blue stars in this photo of M13, and blue stars are generally hotter. And we're going to talk about why that is. All right. Here's another picture. This is an ultraviolet wavelength, 17.1 nanometers. What you're looking at here is the part of the solar atmosphere. This is the sun. This is our star. And this was taken last night about 8 p.m. By the SOHO spacecraft. So this is false color. It's ultraviolet, so which we can't see, but they color everything blue. Where it's really bright is where it's really hot, so about 1,000,000 Kelvin. All right. And we're going to talk about why. And notice that all the features here, it's not a perfectly smooth surface. There's a lot of convection in the solar, all kinds of stuff. It's a real maze of trouble in the solar atmosphere and the surface of the sun. Okay, so this is from the SOHO spacecraft. If you look up the word SOHO and solar on Google, you'll get to their website and you can look at every day they take these pictures like every 3 or 4 hours. So you can look at them anytime you want. It's kind of cool. Anybody know where this is? Anybody ever been here? One of my favorite places on the planet. It's Virgin Gorda, down in the British Virgin Islands. This is the Baths. And all those rocks are volcanic. They're igneous rocks. Igneous rocks come to the surface because of convection in the mantle of the Earth. Here's another hot spot, Yellowstone National Park. Did you know that there's hundreds of little tiny earthquakes out there, tremors, every year in Earth? You know, I went to grad school just a little bit north of this picture in Bozeman, Montana State. And not too far from there is off to the upper left is Missoula, Montana. And I remember at Missoula, Montana, they had a monitoring station, a seismograph, that monitored all the earthquakes underneath Yellowstone. So this is a picture from this article in Nature. Journal of Volcanology and Geothermal Research, R.B. Smith et al. Geodynamics of the Yellowstone Hotspot and Mantle Plume, Seismic and GPS Imaging, Kinematics, and Mantle Flow. What do they mean? Well, here's a cross-sectional view. The top of this is Yellowstone. All right, so here's a little picture up here in the upper left, the Norris Geyser Basin, and then over here, Yellowstone Caldera. Did you know that Yellowstone is actually a huge volcano that blew so hard many thousands of years ago that it completely leveled itself? And all the lakes and stuff and all the geysers in Yellowstone that are so beautiful now are really the remnants of this huge volcanic explosion. And now they're all covered over with trees, and the buffalo live there, and deer and elk and stuff like that. It's a beautiful place. Well, this is what it looks like underneath. Now here's the mantle plume that they're talking about. See this kind of reddish thing here? This is another cross-sectional view. They get this view by looking and analyzing. It's kind of like sonar. Submarines at sea, they're looking for Russian subs or something like that, or they're looking for whales. They analyze sonar. And the same thing here, but they're analyzing seismographs, which is like the sound of earthquakes and stuff propagating through the earth. And this kind of trail of red shows you the hot stuff that's percolating up to the top and comes to the surface at Yellowstone. And here's another view of it from a different angle. Here's the third view. The Yellowstone, this is what they think the Yellowstone mantle plume is doing. It starts down here near the core of the Earth, and it circulates upward and kind of curves around a little bit and eventually comes up at Yellowstone. Now, Yellowstone is right up here. If you look at the word 120 degrees, that's approximately where Seattle is. Over there on the right of this wedge-shaped map, that's about where the Mississippi River is. So the curve of the entire North American continent underneath the western half of North America is the Yellowstone mantle plume. And it is a huge heat transport phenomenon, specifically convection. All right, now let's get down to the nitty-gritty of heating and cooling. And this is the heat melt heat concept. All right, so let's get down to some notes. Liquid water. A calorie is a metric unit of energy, and it's defined as the amount of energy that will raise 1 gram of liquid water by 1 Kelvin, or 1 Celsius degree. All right, so it could be a calorie from sunlight or any other heat transport method. Right? 1 calorie is equal to 4.184 joules. Let me repeat that. This is what James Prescott Joule figured out back in the 1800s. He was able to add some MGH energy. He dropped some weights, caused some motion in the water with some paddle wheels, and he figured out every 4.184 joules that I add, each gram of water will raise 1 gram of water by 1 Celsius degree. All right, so that defines the calorie. Okay, so the specific heat of liquid water is therefore written down as 1.00 calories per gram per Kelvin, right? Because it takes 1 calorie to raise a single gram by 1 Kelvin. Now, sometimes you'll see this written down as 1.00 calories per gram Celsius degree, but I like to use Kelvin. So I'll always use this, okay? And that's the specific heat of water. Every substance has a specific heat. And matter of fact, every phase, every state of matter for a given substance has a specific heat. So, for instance, solid water, ice, has a specific heat of 0.50 calories per gram Kelvin. All right, so we would write down C equals 0.50 calories per gram Kelvin for the specific heat. And what this does is it encodes how easy or difficult it is to heat something up. Okay, some things, like metal's pretty easy to heat up, usually. All right, the water is actually pretty hard. It takes a lot of energy to raise water up by 1 Kelvin. All right? Now, I want you to think, what is the difference between a gram of liquid water, like a droplet of water, and the same amount of H2O but frozen? Well, the difference between liquid and solid phase is that above 273 or below it, you have different bonding between the molecules. If you're below 273 Kelvin, your water is solid, and they have bound together in crystalline bonds. Okay? And my wonderful students, those bonds are electrical potential energy. You've got the molecules have slowed down just enough that they can start bonding together. Okay? And that bonding, it requires work to break it. So what it means is when they form, they've stored energy. Okay? And so we think of those crystalline bonds as stored energy. And you can do the same thing for any other substance that's been measured. And my wonderful students, I remember the specific heat of liquid water, 1.00 calorie per gram Kelvin, simply because that's the definition of a calorie. But everything else I got to look up. So you'll be given stuff, specific heat on the cover page of exam 2. When you're working with specific heats and heat, melt, heat, I'll give you all the specific heats and stuff that you need. So don't worry about that. Okay? And just to reemphasize, the intermolecular bonds are important. Now, liquid water does have some binding. It has some cohesive forces, the forces of cohesion that make it into a spherical droplet. There is, and surface tension. There is a little bit of bonding between molecules at that temperature. But only when they get below 273 do they actually lock tight into a crystalline structure. Okay, above that, they're liquid. And then, of course, above 373, the boiling point, there's no structure at all. It's completely random. It's a gas. A gas has no binding. Now, when I say that you have to look stuff up on a table, this is from a cover page on a recent exam. Okay, you don't have to write it down, but just relax about having to memorize stuff like this. In web courses, if I give you a homework problem, I'll give you this. In class, if I give you a problem to work out, I'll give you these things for clicker questions. Okay, so, and on the test, this will be on the cover page. So specific heat, calories per gram Kelvin. And then this column is called the We're not done. We're not even close to being done. All right? We still have a bunch of important notes to take. In fact, we're going to have really important notes here in just about 2 seconds. This column over here, the latent heat. Now, latent heat is the amount of calories per gram in those intermolecular bonds. You have to add this energy in order to break those bonds. So when you're breaking up when you're breaking up a gram of ice at 273 and you're trying to turn it into liquid water at 273, you got to add 80 calories of work. You got to break them apart. Bust them up, all those intermolecular bonds. So let's do a calculation together, and this will be the last 5 minutes of class. And what we're going to do is make a cup of tea for a polar bear up north. This is a heat melt heat problem. So here we go. How much heat, how many calories, is required to convert 400 grams of water that starts out as ice at initial temperature 268 Kelvin to liquid at 373. So that's now it's boiling water. Okay? So we're making tea. You got to boil the water before you put in the tea. Okay? So this is our task. 400 grams of water. All right? And it starts as a solid. So the specific heat is going to be 0.5 calories per gram. And then we're going to get it up to 273. Then we're going to melt it all. And it's going to take 80 calories for every gram to melt it. Even though it's still at 273, you can melt it. Now it's at 273. It's all 400 grams of water and it's liquid. Now you got to raise its temperature again up to 373. Let's work it out. Okay, latent heat of melting for H2O, 396 kilojoules per kilogram or 80 calories per gram. That's the one that we're going to use. Now the specific heats for ice, 0.50 calories per gram Kelvin. And for liquid water, 1.00 calories per gram Kelvin. All right, so our strategy for heating up this water and making some tea for our friend the polar bear is to heat the ice up. First we heat it up from 268 to 273. All right, so add that to your notes. From 268 to the melting point, 273. And then we melt it. And when we're melting, we're adding energy, but the temperature doesn't change. The phase is changing. If you're adding energy to it, if you've got a fire underneath it, it's going to stay 273 until every gram is melted. And then we go from 273 all the way up, 100 Kelvin, up to 373. All right? So that's our task. Let's do it. All right? And then we'll dismiss. All right? So here are the two equations. For heating, the amount of heat energy is usually symbolized Q, capital Q. It's equal to M, the mass, times C, the specific heat, times delta capital T for the change in temperature. For melting or freezing, it's the mass times the latent heat. So however many grams you've got, 400 grams, times 80 calories per gram. So each one needs 80 calories to melt. And that'll tell you how much you need. Now, here are our temperatures. 268 initial, 373 final, and in between them is the phase transition at 273. We're heating up by 5 Kelvin to 273. And then we have a second stage where we heat up from 273 to 373. All right? And then in between those two, we have the melting stage where we melt all of it. All right, here we go. First one, to heat up the ice. So make a note, this is ice. 400 grams of ice that we started with. Specific heat of ice, water ice anyways, 0.50 calories per gram Kelvin. And how much do you heat it up? You're going from 268 to 273, the melting point. So that's 5 kelvins. And that works out to 1,000 calories. The second heating phase is another 400 grams, but this is liquid water. So the mass is 400 grams. The specific heat now is 1.00 because it's liquid water. And we're heating it up 100 Kelvin from 273 all the way up to the boiling point, 373 Kelvin. So that delta T is 100 Kelvin. And that works out to 40,000 calories. Right? So quite a bit more energy needed. Now, in between those two heating steps, we have to do the melt. Okay, here's the melt. How many grams you've got times how many calories each gram needs to break apart those bonds. And at the freezing melting point, it's 80 calories. For a gram of ice, you need to add an 80 calories of energy to make solid water into liquid water, gram for gram. And you've got 400 grams. So this one works out to 32,000 calories. So the total is 73,000 calories. All right. Now, homework 11 is going to activate tonight. It's not going to be a huge one, but I am going to put a heat melt, at least one heat melt heat question in there. All right. So be ready to tackle that. All right. 11:51. We went over a minute. You're dismissed.
I have an exam review on Thursday, so if you could announce it for the next class.